Now we move on to talk about acids and bases. So I do like James Bond, and so James Bond can hide acid in a gold pen, and well, one of the reasons why gold is so powerful, expensive, is because it's very unreactive, and there is no single acid that will dissolve gold. Although you can do a mixture of something called aqua regia that will dissolve gold. But it's important that he carried this in a gold pen because it otherwise it would dissolve the other metal. There's very few metals that will not be dissolved by acid, and gold is one of them. And of course, James Bond, of course, he does something gold. So you can squirt the bars with some acid, and then the acid eats through the bars. And that's one of the properties of acids, is that it eats metals. Well, specifically, it turns it generates hydrogen gas. So, and it can happen rapidly. So you see here is aluminum can dissolve in hydrochloric acid, and it can dissolve in 10 minutes. That's pretty fast. So let's talk about acids. So some properties of acids. Acids taste sour. So we humans, we generally speaking, we don't like the sour taste. It generally means that the fruit is not is not ripe yet, and so we don't like the taste. Humans also don't like bitter taste. Humans tend to like the the um, the sweet, the salty, the umami tastes. Uh, there's also some starchy taste. I think some of it is also physical properties that we enjoy, but generally speaking, we don't like the acidic taste. It's a sour. It's a very very strong thing, and that's part of our taste as a chemical sense. So acids taste sour. They dissolve many metals, and the ones that they don't dissolve are the ones that are usually really expensive. It turns litmus red. So sometimes you see acids, litmus is red, and then conversely you learn bases turn litmus blue. So common acids, hydrochloric acid. This is also the primary acid in our stomach. We use it quite a bit in chemistry class. Our bodies also make it. And sometimes if you have acid reflux, you can taste the sourness of the hydrochloric acid. Sulfuric acid is one of the highest produced chemicals in the United States. It's the most common. If you want to know what the most commonly produced chemical is, it's fuel. We generate a lot of fuel. The second highest is fertilizer, and that's what we use sulfuric acid for. Is we use it to make fertilizer. So we our agriculture is industrially based, and we generate a lot of fertilizers behind only fuels as far as types of chemicals. So that's, if you're wondering what we use acids and bases for, primarily is fertilizer. We use it for other things too. So we use these in chemistry lab as well. Use it for many, many processes. Also, automobile batteries, they're lead acid batteries, and so they have sulfuric acid in them as well. So if you ever pick up a battery and hear it slosh, slosh, slosh around, it's because it's the sulfuric acid that's in it. So be very careful with them. That's very dangerous stuff. So other common acids, acetic acid, that's what's in vinegar. Carboxylic acid, this is, well, when carbon dioxide reacts with water, it forms carboxylic acid. That's used in fizzy drinks. Our body uses it in part as a buffer, which we'll talk later on, and also as a transportation vehicle for carbon dioxide. So carboxylic acid, these are organic acids. So organic means carbon containing. So you see them, it has a carboxyl group in it. So you can see various things, citric acid, for instance, maleic acid. There's many, many others. Vitamin C is ascorbic acid, anti-scurvy acid. So those are all carboxylic acids. So I can see them all over. So we talk about acids. Acid tastes sour. They turn litmus red. Now bases taste bitter, and bitter is a horrible, horrible taste. Most people can't stand it. And bases feel slippery. And the reason for that, which we'll learn later, generally speaking, acids add positive charge and bases add negative charge. and all biological surfaces are negatively charged. So you add electron density, since something's already negative, what does it do? It blows it up. And then because of that, to a biological surface, bases feel slippery. And so the idea it feels slippery, it's only slippery to a biological surface. So it doesn't mean that if something's slippery, it's a base. Motor oil is slippery. It's neither an acid nor a base. It's nonpolar. Sulfuric acid is slippery, but it's obviously an acid. So just because something is slippery doesn't mean it's basic. But generally speaking, something that is basic will form, especially skin, to feel slippery. And if I ever get a base exposure in the lab, what I do is I'll run my fingers under running water and I will rub them back and forth. And I can tell when it's no longer slippery, I've washed away all the base. So that's one of the tricks that you can do to avoid base burns. And base burns hurt. They come a little slower than acid burns, but man, they hurt for a long time. So here's the bases. I already explained how bases feel slippery, but you can see that, maybe you've noticed that for a lot of things. Bases taste bitter, and the thing is that most things that are bitter are poisonous. And some people like coffee, although because caffeine is actually extremely toxic. So I mean, like a cup of coffee has 100 milligrams, so 0.1 grams, 100 milligrams, that's not a whole lot of material. And if you get pure caffeine, you can overdose on it pretty quickly. So caffeine is in fact pretty poisonous, and many of the other plants we'll call later that alkaloids. Plants make them alkaloids. They're alkaline compounds. Alkaline means basic. Acidic means acidic. Basic also, we can use the word alkaline. We can use it interchangeably in chemistry class. So when you hear the word alkaline or alkaloids, you think, oh, these are basic, not acidic compounds. And there's many, many others. So basically, if something is basic, if it's alkaline, it's probably poisonous. So we humans instinctively do not like bitter flavors because of that. I can't even stand a bitter melon. So some common bases, sodium hydroxide, potassium hydroxide. Sodium hydroxide is also commonly referred to as lye, L-Y-E, lye. We use it for quite a few things, and there's the industrial applications right there. Also use it in soap making. Does have soap making on there? It is in there. Oh, it is in there. Never mind. Sodium bicarbonate. This is baking soda. We tend not to use it as an acid anymore. We typically use calcium carbonate or magnesium hydroxide. Those are we used to use sodium bicarbonate, but I guess this is just, we can't give up with that. We don't use baking soda anymore for an antacid because people are afraid of the sodium ions. So, and it would directly neutralize the stomach acid. So Savante Arrhenius came around and he said, all right, let's define acids and bases. This is a very simple definition. If you throw something in water and it forms hydrogen ions, it's an acid. If you throw it in water and it forms hydroxide ions, it's a base. So this is the lowest of the definitions. We're talking about the Bronsted-Lowry definition later, and not in this class. There's also the Lewis acid and base, which we won't really cover. So the Arrhenius acid, for instance, hydrogen chloride is, we've studied this before. It's a polar covalent compound. It looks fine, but you throw it in water, it breaks apart into hydrogen and chloride anions. So it breaks apart, and that's what makes it an acid. And we use this interchangeably with chemistry. The hydrogen ion, you can think of like water as like a Mickey Mouse molecule. If you add an extra ear to Mickey, an extra hydrogen ion, you get like Mickey Mouse with 3 ears, and we kind of call the whole thing being a positive +1 charge. This is the hydronium ion. So this is closer to the truth. Simulations suggest that in an acid, there's not really any free hydrogen ions. They're all bound up into hydronium ions. The problem is, this is something we can never really truly know. Because how are we going to find out? We typically do spectroscopy on things, especially look at electrons. Hydrogen ion is just a proton, doesn't have any electrons. So we can't do spectroscopy, at least electronic spectroscopy on it. We can do like magnetic spectroscopy on it, but it's probably not going to change that much in terms of if it's free or if it's bound to a water. So what the nature of acids are, this is something that's kind of interesting. We may never know. This is something we may not be able to know. So that's kind of cool, right? I like that some things even with our understanding we can't know 100%. We're just kind of guessing. So we use these interchangeably, and hydrogen ion or hydronium ion. I think it's easier to use hydrogen ion. I tend to write out the equilibrium with the hydrogen ion rather than the hydronium ion. Just like I said, it's easier, and it's just one less thing to do because you have one atom instead of four, and it's just easier to keep track of fewer atoms. So I just do it personally. That's my own preference. Although the more accurate is the hydronium ion rather than the hydrogen ion. So we are going to talk about just really, really briefly that if you look at this formula for formic acid, and you can see that there is a hydrogen attached to the oxygen. The idea is that the oxygen in the carboxyl group is a C double bond O OH. That the oxygen atoms, they draw electron density away from the hydrogen, so much so that the hydrogen can easily pop off. Then the hydrogen attached to the carbon, though, is pretty strongly bound, so that's not so easy to break off. That is not an ionizable hydrogen, but the one that's attached to the carboxyl group, the C double bond OH, that is an acidic hydrogen that's very easily ionized. So, and you can talk about more of this in our organic chemistry if you study more and more chemistry, but not every hydrogen in the molecule is the same. You have some acidic hydrogens and some that are not. And so, that's one of the powers that we have as chemists, as we can predict which hydrogens can be ripped off. So an Arrhenius base, so sodium hydroxide, you throw it in water, forms hydroxide ion, so it's an Arrhenius base. So it's also a strong electrolyte, it rips apart. So definition of acids and bases, when they react, acids and bases react, it forms water. So the hydrogen ion plus the hydroxide anion, so these react to form water. So acids and base react to form water. And we'll learn later also they make salts. So a better definition of acids and bases is the Bronsted-Lowry. And the Bronsted-Lowry describes a transfer of protons. So we say that an acid is a proton donor, it's a source of the hydrogen, and a base is a proton acceptor. So, and this aids. It shows how other compounds like alkaloids can be bases. Although if you do throw them in water, they do form hydroxide ion. But it'll apply acids and base reactions to non-aqueous environments. So already mentioned there, Johannes Bronsted. Yes, thank you for your discovery there. And so if you look at hydrochloric acid, HCl is a Bronsted-Lowry acid because it donates a proton to water. And you can see here that this definition works better with the whole equilibrium, that the HCl is giving its proton to water. That makes HCl the acid, and it makes water the base. So water is then the proton acceptor. So to form the hydrogen ion. You see what I mean by that? HCl loses a hydrogen, becomes Cl minus. H2O gains a hydrogen. It's the acceptor, it's the base, forms to H3O. So it's added an H for water, lost an H for HCl. So acid, proton donor, base, proton acceptor. And now look at ammonia. Ammonia now is a base because if you look at this reaction here, NH3 plus water makes NH4 plus OH minus. So that fits the Arrhenius definition because it forms hydroxide in water. But if you look at this, water is giving one of its hydrogens to NH3. So water is the acid, and then NH3, ammonia, is the base. It's accepting that hydrogen. So, and you might notice something we'll talk about later. Water is both an acid and a base. That's kind of weird, but we'll talk about that later. But now if you look at these equilibriums, so here is HCl water. I'm sorry, HCl acid is a proton donor for base. Or for HCl, water is a proton acceptor, and then for ammonia, water is an acid. It's given a proton. So water is special. We give it a compound. We call it amphoteric. So substances can be either acids or bases. These are amphoteric. Is water the only amphoteric thing? No. Amino acids are also amphoteric. So it's not necessarily uncommon, but generally speaking, a lot of things usually go one way. But water can go either way. It's amphoteric. So, and you can notice in this equilibrium here, ammonia plus water to form ammonium and hydroxide. So in the forward reaction, ammonia is the base. It's the proton acceptor. But if you look in the reverse reaction, NH4 is losing a proton, so it's a proton donor. So in this case, ammonium is an acid, and so we call this term conjugate acid. And water is the acid. It's a proton donor, but if you look at hydroxide anion accepts a proton to form back to water. That's the conjugate base. So you have the full word going forward, and then the conjugate, and then the opposite word. So base, conjugate acid, acid, conjugate base. So that's one of the terms here for Bronsted-Lowry. And I've already described that. And they always go in pairs. So the acids and base pairs, or the conjugate bases, they go together when you do them. And I've already described this is a new equilibrium. So sulfuric acid plus water. Although this is a strong acid, and which we'll talk about later, it's only in one direction. It doesn't go the other way. But if it did go the other way, bisulfite anion here would be the conjugate base, and then hydronium would be the conjugate acid. So this is not an equilibrium, and it is signified by a solid arrow. So for acids and bases, when they react, acids and bases react to form water and a salt. So acids taste sour, bases taste bitter. So what does salt taste like? And remember, taste is a chemical test. Salts taste salty. They're neither acid nor base, at least for sodium chloride, I should say. In future classes, you can learn that salts do tend to be one or the other, but for a strong acid, strong base, it has a neutral salt like sodium chloride. So this is a new flavor. It's neither an acid nor a base, so there's a chemical change there. So that's our proof for a chemical change. So salts no longer carry the properties of the acids and base. So the general reaction then for acids and base neutralization reaction is an acid plus a base forms water and a salt. So, and the net ionic equation, removing all the spectator ions, it's just the formation of water. So, or it'd be hydronium plus hydroxide forms two waters if you want to do the other one. So it's kind of interesting. So what about other things? Like when you have carbonates and bicarbonates, if you react an acid here, you can form gas evolution reactions. So with there are other types of reactions that can go. And so let's write the balanced chemical equation for the neutralization reaction between hydrogen iodide or hydriodic acid and sodium hydroxide. So we have Hi plus NaOH forms water and sodium iodide, all balanced out for the charges. And let's see if everything is balanced properly. So actually it turns out it is. So all the atoms are accounted for, so we are already balanced. So this is an easy one. So another property with acids are when you put them in metals, it forms hydrogen ions. Hydrogen gas. When you put acids and dissolved in water and you put in metals, form hydrogen gas. And so this is the metal plus acid forms a hydrogen gas plus a salt. So you can see here 2 hydrochloric acids react with magnesium to form hydrogen gas and magnesium chloride. So here's a couple of these. So acid plus magnesium and sulfuric acid plus zinc, hydrochloric acid plus iron. And these are all also balanced for you. And you can notice that most of the metals do this. There are very few metals that don't, and those are the expensive ones. And of course, we have to make sure that, like, if you notice the dental implants, there's only certain metals they put in. We usually use silver, gold, mercury. We don't tend to do copper, but you have to be careful what you put in your mouth, because you do have acid in your mouth. So, and you can also have acid coming up from your stomach. So, yeah, you gotta be careful what you put things in. And James Bond there, he made sure it was made of gold, but that's also why we use. A lot of people have gold teeth, and that's because so that the gold doesn't dissolve in your mouth. So, acids can react with metal oxides. So when acids react with metal oxides, they also form water and a salt. So you can see here's several different acids here, and they form water and salt. So also you can see metal oxides are alkaline, they're basic. So what about bases? So we covered a few of these, but sodium hydroxide and aluminum do actually react. It forms a complex. This is not the main reason why we don't use pipes made of aluminum. Aluminum is a very reactive metal, but it has an oxide layer that's really hard. The oxide layer is known as sapphire. It's a very tough material. It's got a 9 on the Mohs hardness scale, so it's a great passivated metal to use. Chloride anion penetrates through this passivated layer. And because of that, and because it takes a little bit of salt to corrode a pipe, then we tend not to use aluminum. You might also notice that we don't have ocean boats made of aluminum. You can have, like, on lakes and rivers, you see canoes made of aluminum, but you do not see that in the ocean, and that's because of the levels of chloride anion in the ocean would just eat the boat apart. So if you're ever wondering there. So that's the main reason why we don't have aluminum pipes. But okay, so now we're going to talk about titration. Titration is just a way that we use to figure out how much stuff is in something. So this is one of our procedures that we do, and this is an old school thing you can do by hand, a little old school procedure. Right now, today, we usually have robots do it. I mean, we do it sometime in the lab, but it's very rare. We usually have robots do this work for us. But if we know the concentration of one thing, we can use that to figure out what the concentration of something else is by how much it reacts. And so, and of course, if we know the chemistry in terms of the stoichiometry, we can figure out all of the amounts and numbers. And also, this is an old school thing, using indicators. You'll see this commonly in chemistry class, especially looking for an endpoint using an indicator. And phenolphthalein is a very common one, so you can see the equivalency point. It's got a pink. It has like if you go too far for the hydroxide, it has a very hot pink, and it's a dull pink for just at its equivalency point. So when you do this, you try to get it to its equivalency point, and it can be it can be hard. It depends. It just depends on what it is, but sometimes even more than a drop will just go right past the equivalency point. Be careful with phenolphthalein, though. Although you can use it in small amounts, it's a very strong diuretic. So that's one thing about phenolphthalein. So be careful if you use it. So equivalency point, I use that term for it's when the moles of acid equals the moles of base. So that's the equivalency point. It's also, if you are studying calculus, it's where the second derivative hits 0. So if you are studying calculus, or you're going to study calculus, you can remember, why are we doing all this stuff? One of the definitions of an equivalency point is an inflection point is also when the second derivative of the function equals 0. So you can think about that if you take future classes in calculus. So for the lab though, and this is just in general, it's the purpose of titration is to figure out how much the concentration of what you have. And so we know the concentration of one, so we do the reaction to figure out the equivalency point where the moles of acid equals the moles of base, and then we can figure out what the concentration of the unknown solution is. So it's a very useful tool. And also, you have to understand the chemistry, in terms of the stoichiometric ratios. So keeping in mind the number of protons, the number of hydroxides to make sure that you're at the right amount. So you have to have some general knowledge to understand what the material is that you're doing. Many of them are 1-to-1, but there are also many that have more than one. So you have to be careful. So let's do a calculation example for this. So titrate 10 milliliters of hydrochloric acid unknown solution. It requires 12.54 milliliters of a 0.1 molar sodium hydroxide solution to reach the equivalency point. What's the concentration of the acid solution? So we know the volume of the unknown solution, and we know that it takes 12.54 milliliters of a 0.1 molar sodium hydroxide. And so with this, we know the reaction. That's a 1-to-1 molar ratio. So if you know the chemical reaction, it's a 1-to-1 molar ratio. And so now from this, we're going to have to figure out the number of moles of sodium hydroxide. So from that, we know how many moles of sodium hydroxide. And then that's at the equivalency point, it's going to equal the number of moles of hydrochloric acid. And then we take the moles of hydrochloric acid divided by the volume of hydrochloric acid, which is 10 milliliters, and they'll tell us the unknown concentration. So there's what I just described, and let's go ahead and do that. So and you can do it all one fell swoop if you want, and just make sure the units all cancel, and do the dimensional analysis. And from this, that's this one here, I guess you get the moles and the moles per liter, and then you get the 0.125 molar for the concentration of the unknown hydrochloric acid solution. You could even, if you want, you can even do this all in one straight equation. You could divide by the 0.01 liters, or you can, if you're good enough in math, just multiply it by 100. In this case, you can multiply it by 100 if you're just going through. So to get the answer. So check the answers. Does this make sense? Well, let's think about it. So it took 12 milliliters. I'm not even looking at the numbers, but I know it took 12 milliliters of 1.1 molar. So that tells me that the concentration of the unknown acid is higher than the original, but it's not too much higher. It's close, but it's slightly higher. So yeah, this makes sense. It's close but slightly higher. So this seems right. So let's talk about strong and weak acids and bases. So hydrochloric acid is a strong acid. It completely breaks apart. Hydrofluoric acid is a weak acid. It does not ionize the solution. So what's going on here is weak acids, these are like disgusting couples. Okay, like you ever seen a disgusting couple? They are always next to each other. You go out somewhere, they're always together. You go to a party, lots of people. They are sitting next to each other. They do not want to leave each other. And sometimes they do leave each other, but as soon as they leave each other, they come right back to each other. Right? So that is a weak acid. Weak acid likes to stay bound. So strong acid, though, these are like the completely no feelings. You have that friend, you go to a party, friend just first, as soon as you walk in the door, friend's just gone. And the friend is running around, bumping into everybody, talking to everybody. That's a strong acid. Strong acid, there is no binding. They just leave. Weak acids, though, these are more bound. And so the hydrogen is much more bound to it. And so but you'll see it's strong acids. You're like, well, wait a second. Fluorine is a halogen. Why isn't it a strong acid? It's because hydrogen fluoride kind of in solution forms a dimer. So this whole dimer, it kind of holds hands with itself, and then that makes it a weak acid because it's so attracted to itself. The hydrochloric acid and the rest of the halogens do not form this dimer, so they just fly apart. So if you're wondering what's so special about hydrofluoric acid is a really scary acid, by the way. It will dissolve your bones. It'll eat through your skin and dissolve your bones, and you won't be able to feel it. And because it is also, at first at least, because of the surface, anesthetic. So scary stuff, really scary stuff. So, but anyways, back to hydrochloric acid. It just breaks apart in water. Like, this is your friend, goes to a party, just leaves. It doesn't stick around. So hydrochloric acid, strong electrolyte, does not have really that much of care or concern for the chloride anion. It just breaks apart and forms hydronium ions. And strong acids are also strong electrolytes. So that means they will conduct electricity. Pure water is a weak electrolyte, does not conduct electricity very well. And then let's talk about strong acids. And I hate to tell people to memorize things, but the easiest thing is to just memorize the strong acids, and then everything else that's not listed here is a weak acid. So rather than memorizing all the weak acids, just memorize the strong acids, and there's only 6 of them, and then everything else is a weak acid. And 5 of them are monoprotic. So mono means one, proton means the hydrogen. So the good old protium hydrogen. So monoprotic acids, there's only one proton. And there are many diprotic acid. That means there's 2 acidic hydrogens. So sulfuric acid is one, H2SO4. So the 2 hydrogens there are both acidic, and it's a diprotic acid. So here are the strong acids. And although I must also say it's only the first hydrogen in sulfuric acid is a strong acid. The HSO4 minus, that is also an acid. It's a weak acid. It tends to stay more bound. Although it's a pretty strong weak acid, it's still that. So I already mentioned hydrochloric acid, hydrobromic, hydroiodic, not hydrofluoric, nitric acid, perchloric acid, and sulfuric acid. So primary use for all of these is actually fertilizers and some explosives. So perchloric acid, some of the cheap fireworks, they use perchlorates. Perchloric acid tends to make explosive things. Primary use, for both nitric acid, sulfuric acid is fertilizer. Hydrochloric acid, we also refer to it as muriatic acid. So if you hear the word muriatic acid, we mean that. We tend not to use hydrobromic acid or hydroiodic acid as much. We don't see those frequently in industry, but we do use them sometimes. But generally speaking, we tend not to use those. But we do use especially sulfuric acid in large quantities. So hydrofluoric acid is a weak acid. It tends to stay more together. So it's the disgusting couple, right? Holding hands. They do not want to break apart. That hydrogen does not want to leave its couple. It's really, it should be H2F2 kind of thing. But I mean, it's just, you can know it's a weak acid. It's a dimer. And but it really doesn't really break apart. And if you see this image here, it's a weak electrolyte. So, and the strong electrolyte, the light bulbs on the right here is hydrofluoric acid. It's got a dim light bulb. The strong electrolyte has a very high light bulb. It means the solution conducts electricity really well. For a weak acid, it's a weak electrolyte. It does not conduct as well. So get the dim light there. So lots of common weak acids. Carboxylic acids, and there's a lot of them. Maybe you hear there's fatty acids. Those are carboxylic acid. They're organic compounds, mean are carbon containing. So there are many, many, many carboxylic acids, and some of them are diprotic. There's triprotic. There's even tetraprotic. So ethylene diamine tetraacetic acid, for instance, is a tetraprotic acid. So you have lots of things going on here. So there are not listed in the strong acids. So sulfurous acid, so H2SO3, carbonic acid, H2CO3. These are weak acids, and phosphoric acid, H3PO4, is still a weak acid, and so they tend to stay together. And I already mentioned the second hydrogen not being strong and sulfuric. So here are some common weak acids the scary, scary hydrofluoric acid, acetic acid, good old vinegar, formic acid. This formic actually refers to ants. It's the one of the toxins commonly found in ant bites. So interesting stuff. And so phosphoric acid, we also use that for fertilizer. So you can see there's a common theme here, right? We use a lot of our chemical know-how to grow crops. And that's the reason why our population is measured in the billions now, because of that ability for our industry to support such a large population that we can feed them. So let's determine the hydrogen ion concentration or hydronium ion concentration of acid solutions. So do this in molar, 1.5 molar HCl. So this is strong acid. It's straight away it's 1.5 molar. So 3 molar acetic acid. This here, acetic acid, is not one of the 6 acids we had memorized to be strong acid, so it's a weak acid. That means it's going to be less than 3. So 3 molar, it is actually very significantly less than 3. It's probably closer to 0.001 molar, to give you an idea how little it breaks apart. So yeah, vinegar tends to have a pH of around 3, and that's actually very concentrated vinegar, but it's probably going to be somewhere between 2 and 3, so 0.01 to 0.001. So it's not it's going to be significantly less than the 3 molar. Then 2.5 molar nitric acid, that's a strong acid, therefore it's straight 2.5 molar. It's the strong acid that it just breaks apart. And this here shows you the thing I said there. So what about, so you can try this for yourself. So the thing here, if you do it yourself, B is a strong acid, the other 2 are weak acids. So some strong bases, we mentioned some of these before, and I guess we didn't talk about lithium hydroxide as much. Lithium, we have to be a little careful, because if you take lithium can be psychoactive. So at least as far as consumption, but we use it in things like batteries, of course. Although I don't entirely agree with the book here, given strontium, calcium, and barium hydroxide. I mean, you can drink calcium hydroxide, and it's not going to harm your stomach. I wouldn't drink barium hydroxide. Barium is very toxic. I don't know about strontium. Strontium is a little more rare. And although I don't think I should drink lime water anyways. You definitely don't want to drink any of the alkalis, the lithium, sodium, potassium. These will clean you out. I mean, you'll die pretty rapidly from the ulceration of your esophagus and stomach. So you do not want to drink these. The alkaline earth hydroxides, they are a little less powerful. But the other thing that's interesting, I mentioned salts being acidic or basic. The alkaline earth salts, they behave like strong bases there. So it's a interesting thing. They're not terribly soluble, and they're still, they can be dangerous. You do not want to put calcium hydroxide. I said it's not a very strong base, but if you put that in your eyes, it will blind you. So it's kind of a weird thing. You can drink it, and it can be okay, but you put it in your eyes, it'll blind you. So it's, I don't know. I guess the point of the thing is to be cautious. Oh, and also similar to acids, the alkaline earth hydroxides have 2 hydroxides, and the alkali metal hydroxide have 1. So keep that in mind. So strong bases, they form strong electrolytes, just like the strong acids. Weak base is similar to a weak acid. It tends not to shift. The equilibrium tends to shift towards the base being just bound together, not necessarily broken apart. So the equilibrium tends to shift to the left towards the reactant side, and because of that, it's a weak electrolyte. So ammonia, for instance, is a weak base, and it's easy, similar to the acids, it's easy to remember the strong acid, strong bases. It's really just the alkalis and alkaline earths. So debatable about the alkaline earths, but if it's not one of those 2, it's a weak base. And it's a base, it's a weak base. So it's pretty easy for you to remember, right? That's just kind of 2 things versus the 6 you kind of have to remember for the strong acids. So there are many weak bases. And amines, what are organic amines? Organic amines are carbon-containing compounds that include nitrogen. So you can see here, like pyridine there, it's got a carbon in it, it's got nitrogen, and maybe you'll think of some of these things. So there's methylamine, smells like fish. Ethylamine also smells like fish. A lot of the amines, I don't like amines, they stink. So they're really smelly compounds. They all smell like stinky fish to me, or decaying, death and decay. So cadaverine is another amine, right? So I don't like working with amines. They're smelly. But besides the fact they're smelly, they're also weak bases. So when you hear these words, you'll start to think about some of the words like we'll talk later about amphetamine. Amphetamine is amine. It's an amine. It's a weak base. Also very toxic. So you can see here these weak bases are alkaline. They also tend to be toxic. So okay, let's do the hydroxide ion concentration of these things. So 2.25 molar potassium hydroxide. So this is a strong base. It's just straight 2.25. 0.35 molar methylamine. So this is a weak base, which means it's going to be significantly less than this 0.35 molar. It's going to be very, very small concentration of hydroxide. C is a little more interesting. So 0.025 molar strontium hydroxide. Also, you can see strontium hydroxide is not terribly soluble, so that's why it's such a low number. But the problem is that there's two hydroxides. So the hydroxide ion concentration in this is going to be 2 times 0.025. So that one's going to be 0.050 molar hydroxide ion concentration in that. So you got to double it because there's a 2 there behind the strontium hydroxide. So keep that in mind on if you're doing stoichiometry with these and looking at the chemical reactions, make sure that you include the 2 there. And there's going to be twice as many units of hydroxide as there are per unit of strontium hydroxide. So which is here, which I mentioned. Okay, you can try this and note that sodium hydroxide is a strong acid. I'm sorry, it's a strong base. It's a strong base. So is barium hydroxide, and the pyridine there is a weak base. So, but don't forget with the barium, there's going to be double the hydroxide with that. So also mentioned with water is amphoteric. It is both an acid and a base. So water can then react with itself to form hydronium and hydroxide ions. And this is called self-auto-ionization or auto-ionization. So I've heard both. And at 25 degrees Celsius, the auto-ionization of water and the hydronium ion equals the hydroxide ion concentration. And this is 1 times 10 to the minus 14 is the concentration here. This is also known as the Kw for water. So in a neutral solution, the acid equals the base, the hydronium equals the hydroxide. So, but this relationship, this equilibrium for Kw, this holds true for all water at 25 degrees Celsius. So if you change the temperature, then you change the equilibrium. So, but that's for future classes. So you can use Kw in the calculation, calculate the hydroxide ion concentration, and determine if it's acidic, basic, or neutral. So for A, we're going to take this number. I guess I'll share the math. So we'll do all these. C is easy. If you look at that, it's going to be 1 times 10 to the minus 7. That's a neutral solution. So for A, this one's slightly greater than 10 to the minus 7, so that's an acid. B is a base, and I can't do the math at the top of my head. Let's look at the math here. So for A, use the Kw equilibrium and take Kw divided by 7.5 times 10 to the minus 5. We get 1.3 times 10 to the minus 10. And so this is an alkaline solution there. I'm sorry, it's not alkaline. I'm sorry, it's acidic solution. This is an acidic solution. There's much more hydrogen ions than there are hydroxide ions. For B here, this is hydroxide ion solution is a little higher, and it's higher than 10 to the minus 7. Therefore, it's alkaline. It's a basic solution. And C, it's neutral. And you can try these similar logic, but you're gonna look for acid. And same logic applies, except that if it's greater than 10 to the minus 7, it's going to be and remember, greater means the lower negative, so -2 is a bigger number than -7. So I know you guys, that's a little tricky, but they'll tell you if it's acidic, basic, or neutral. So let's summarize at 25 degrees Celsius. Hydronium and the hydroxide ion concentration are the same at 1.1 times 10 to the minus 7 molar. Acidic solution, it's greater than 1 by -7, and then a basic, and hydroxide for an acid is lower than 10 to the minus 7, and then the opposite is true for the base. And for all solutions, the concentration of the hydroxide times the hydronium is equal to 1 times 10 to the minus 14 at 25 degrees Celsius. So change the temperature, this number does change. So you can see here acids and base, and then you can have stronger acid, stronger base, more hydroxide, more hydronium ion, depending on where you are in this. But this is an easier way to do it, and we typically use something called pH. So we use the pH scale, and it makes it a little easier. And if it is less than 7, it's an acid. Greater than 7, it's a base. Equal 7 is a neutral. And so pH makes things easier versus looking at things and doing all the math. And here's a pH scale, and this is also known as a logarithmic scale. So a logarithmic scale where we each factor stepping up by 1 is actually by a factor of 10. There's other logarithmic scales. Sound is a logarithmic scale. So when you go from 90 to 100 decibels, you are not going up by a little bit, you're going up by a factor of 10. The Richter scale is also a logarithmic scale. So it actually, in energy-wise, you're going up by a factor of about 30 for Richter scale, and that's based off of the average density of rock. So we assume an average density of rock for the Richter scale. So there are other logarithmic scales other than pH. So, like decibels, like Richter scale, and pH. These are all logarithmic scales. So the way that you calculate pH is you take minus log base 10 of the hydronium ion concentration or hydrogen ion concentration. Use those interchangeably. So you just take the number and you just type it in the calculator, minus log that number, and you press enter, and then you get the value. And that value is the pH. So you can't have a negative pH, because if you have a concentration of 10, the pH is -1. So that's one thing with it. The pH, we usually have 0, but log is 0, or 10 to the 0 is 1. So that brings us close to 1. So let's do the calculation here for the part A, minus log of the hydrogen ion concentration. We get 3.74. So something to note with the units. So for pH, the units after the decimal point are the ones that are significant. So you can see the 3 is not considered to be, in 3.74, the 3 for pH is not considered to be significant, because that's the exponent. So everything right of the decimal point are the significant figures here. So same one for part B. Take minus log of the hydrogen ion concentration, get 8.14. That still has only 3 sig figs, because the sig figs are to the right of the decimal point. So another thing for you to remember, right? When you think things are getting easy for you, guess what? You got another rule to remember. Gotta love chemistry, though. So how do we go from hydrogen ion concentration from pH? I tend to do method 2. So I just do 10 to the minus pH, and then pop it out. You can do the inverse log all as well. I just do the 10 to the minus pH to get it. So it's however you want to use your calculator. So calculate the hydronium ion concentration with a pH of 4.80. So 10 to the minus pH, and you get 1.6 to 10 to the minus 5. And remember, the sig figs are significant to the right of the decimal points. That's 2 sig figs. So, and you can do this on your own. And you can also do, for part B, you can also do pH plus POH, and you can have the same thing with pH. You have POH is 14, and you can do it that route if you want, if you don't want to go through the kW calculations. So let's move on and talk about buffers. Buffers are an interesting series of compounds. They typically have weak acid and its conjugate base. You can use a weak base and its conjugate acid, but we tend to do it more with the weak acid conjugate base. And in a buffer, the pH, when you add acid or base, it doesn't change very much. And the buffer, the acid and the acidic and basic nature of it doesn't really move. And it's really, buffers are used when you don't want the pH to change very much. And one of the examples of that is the human body. We have a sodium bicarbonate and carbonic acid buffer in our bodies. That's how we regulate our pH. It's we're a little alkaline, not too alkaline, but we really, really need to be at a very narrow range, 7.36 and 7.4. If we change too much, we can die pretty easily. And what's also interesting is that we use carbon dioxide as our buffer. So we use a waste gas, right? And we use the waste from our respiration as a way to regulate our blood pH. That's kind of cool. You talk about how efficient the human body is, right? That's kind of cool that we use something like that. And also when people hyperventilate, hyperventilation there, what happens is that if you hyperventilate, your blood's pH goes up. It becomes more alkaline, and you get a case called alkalosis. So when people are hyperventilating, you give someone a bag to breathe in. Why are you doing that? And that's actually to absorb the carbon dioxide back in. So, because you need that carbon dioxide, our body needs this at a certain level. In extreme cases, you can inject sodium bicarbonate into the patient. So baking soda. And it's got to be really pure baking soda, and it has to be done in a hospital, right? So don't do this at home, but that's what they do for extreme cases. Oh, I should say of acidosis. For alkalosis, most people just hold their breath, and then you generate more carbon dioxide, and that tends to cure that. But okay, so for instance here we have acetic acid and sodium acetate buffer system. So we have the combination of these two, and if you add acid to it, you will form more. The acetate will react to form acetic acid, and if you add base to it, the acetic acid will react to form more acetate. So it's kind of nice. It keeps the pH not changing very much, and then because of that, the pH stays relatively constant. So this is a nice thing about pHs, about buffers. The calculations are kind of tough, but you can learn how to do that in the future classes. You can use something called the Henderson-Hasselbalch equation. It's not too bad. So I already mentioned here alkaloids. And so alkaline, right, means basic. Alkaloids, these occur naturally in many plants. And these are usually toxic. And you also see them in small amounts. So I already mentioned things like caffeine, nicotine. Here is morphine. Morphine is an example of something that it's a narcotic as well. So it is highly addictive. It's also a small amount can kill you. Not only the fact that you don't need much. So amphetamine is another one. So many things. So like methylamphetamine, right? So the amine, the carbon-containing nitrogen compound. This is an alkaloid. So and these do many other things. So be careful if you use these. This can be dangerous. So and one other thing to end it is antifreeze. And so the thing with antifreeze, it's got the OH on them. It tastes sweet. So antifreeze tastes sweet, and problem is animals like to drink it. So dogs and cats, like they like eating this, and the problem is it turns into glycolic acid. If you eat ethylene glycol antifreeze, it turns into glycolic acid, and then glycolic acid can overpower our blood's buffer system, and then it causes the pH to drop. And one of the things is it limits our ability to carry oxygen. It can also denature some proteins. And the cure for this is sodium bicarbonate. It's a solution of sodium bicarbonate to neutralize the glycolic acid, and then you have to monitor the patient, the cat, the dog, or the human, make sure that the blood's pH is at the right level, and adjust the bicarbonate solution to make sure that the blood's pH doesn't drop too far, and then just keep on going until it all goes through your system. If you must know a simple cure, one of the ways to get around this is to get really drunk. There's a few cures. If you can at least slow it down by administering alcohol to the patient, although humans are a little more receptive to it than animals. Other primates would do it, but cats and dogs tend. I guess dogs do like beer, but it's give the patient some alcohol. Don't give a cat red wine though. I mean, that can kill the cat. But that is another way. But you still need to get medical help with that though, because you need to get the that just buys you more time. So you still need to get to the hospital. So, but if you do accidentally drink some antifreeze, that is a quick fix. And the reason for that is that your liver will go for the ethanol before it will the ethylene glycol. As far as the attacking of it and turning it and oxidizing it to the glycolic acid. So review: acids taste sour, dissolve metals, form hydrogen gas in metals, turn litmus red, bases taste bitter, feel slippery on biological surfaces and turn red litmus blue. Arrhenius, you throw if an acid in water forms hydrogen ion, it's an acid. If you throw it in water, it forms hydroxide, it's a base. Bronsted-Lowry, acids are proton donors, bases are proton acceptors. When you react acids and bases, you form water and a salt. You can also react with metals to form hydrogen and a salt. You can also form metal oxides to form water and salts. And titration is a way to figure out how much stuff is in stuff. And you have to know one of the two, though, to be able to make it work. Strong acids you have to just memorize them: hydrochloric, hydrobromic, hydroiodic, nitric, the first proton, and sulfuric and perchloric. Those are the 6 strong acids, and everything else not listed is a strong base. As a weak acid. The strong bases, they're the alkalis and alkaline earths, basically. And but the alkaline earths are not very soluble. The alkali metals are much more soluble. We learned about the self-ionization of water, the pH and the pOH scales, more on the pH scales. We use the pH more than the pH scales. And briefly talked about buffers, because buffers are a way of keeping the pH consistent in a system. Oftentimes it's biological, but it can be for other reactions too. And so you can pick your buffer to keep the pH at a consistent level. And it contains it's a weak acid and its conjugate base. Here are the learning objectives and the legal. And thank you again for listening.